Welcome everyone to part 3 of NeuroSymbolic methods for creative text generation. We talked about generating sarcasm and simile and showed how common sense knowledge is really important for these sort of figurative languages. And of course, the figurative language space is really vast, but the third figurative language which we generate and about which we have published papers at this year NACL and upcoming paper in ACL is metaphors. So in this part of the talk, I'll be talking about how we can generate metaphoric paraphrases or metaphors. And this is work done with my advisor, Violet Peng, and my colleague, Shurui, presented at NACL. And before I actually go on to give the talk, we have a funny video of a demo, so I would like to share that with everyone. So take a look at the demo. And I'm really excited to talk to you guys today about more metaphor generation with symbolism and discriminative decoding. And this is work done in joint collaboration with Zurui, my PhD advisor, Smaranda Murishan, and my frequent collaborator, Violet Peng at UCLA. So metaphor is a figure of speech in which a word or phrase literally denoting one kind of object or idea is used in place of another to suggest a likeness or analogy between them. As you can see the example, you are drowning in a student loan debt, or lightning danced across the sky. And I cannot go on to give this talk without mentioning Milan Kundera's famous quote, "Metaphors are not to be trifled with. A single metaphor can give birth to love." So the goal of our project is to generate metaphors to promote more creative energy output. And this can be used to make dialogue agents more engaging and also used as human-in-the-loop tools as writing assistants for creative, argumentative, or persuasive writing process. So the task which we here are interested in is, given a literal input sentence, we want to generate a corresponding metaphoric sentence. And the simplifying assumption here is we focus only on verbs as they are often the key component of metaphoric expression as shown in prior work. So you can see this input literal example. The window panes were rattling as the wind blew through them. And our best model generated the window panes were trembling as the wind blew through them. Similarly, for the input, after a glass of wine, he relaxed up a bit. Our best model generates, after a glass of wine, he loosened up a bit. So there is lack of training data, which means there is no parallel literal to metaphorical training data to train a generative sequence-to-sequence model. Also, we need to ensure that the generated metaphorical sentence has the same meaning as the literal one. And finally, we all know that generative language models have a capability of generating more literal text compared to metaphorical text. So we have to handle all these key challenges. And in doing that, we rely on a theoretically grounded relation between metaphors and symbols. So Suzanne Langer, of eminent philosophers, said, "A metaphor is not a language. It's an idea expressed by a language, an idea that in turn functions as a symbol to express something." So our approach here is that first we automatically create a parallel data set of sentence pairs, literal to metaphoric. And in doing that, we first identify metaphoric sentences, that is sentences with metaphoric verbs. We then generate their literal equivalents that is semantically consistent. As a next step, we fine-tune a sequence-to-sequence model here in particular BART on our parallel data, and then we use the discriminator to guide the decoding process instead of relying on the likelihood-based approaches by BART. And finally, we also assess the quality of generated metaphors through intrinsic and task-based evaluations. So to take a look at our automatic creation of parallel data, we first start with a large-scale Gutenberg poetry corpus, which is an online corpus of literary and poetic text. To give you an example, an input sentence is, the house where love had died. So as a first step, we use a BERT model fine-tuned on the VUA metaphoric corpus to identify metaphoric verbs, but then there could be of different quality. So we choose sentences where BERT model predicts the verb as metaphoric with confidence score of 95% to ensure the quality of our data. Now, after we have identified the metaphoric verbs, we need to convert them to their literal counterparts, but also ensure semantic consistency. So for example, you can see the house where love had ended basically is semantically consistent to the house where love had died. But how do we go on and create this? So we can use masked language model infilling to generate verbs that have a literal sense. For example, if you take the sentence and mask the word died, then you can get multiple candidate replacements such as started, originated, been, ended, etc. And what we do next is we take the same model which we used to detect metaphoric verbs, and then we basically rank these MLM candidate replacements using inverse metaphoricity scores, that is literal scores. But we also want to ensure that there is semantic consistency between the literal and the metaphorical verb. To do this, we use an adapted knowledge model, COMET, which is basically a GPT-2 model fine-tuned on ConceptNet, and we employ the symbol of relation. So as you can see here, the house where love had died portrays the symbol of loss, loneliness, despair, sadness, and sorrow, which is consistent with our common sense. Now, as we already described that we want to ensure semantic consistency, there could be multiple candidate replacements from the MLM. So two examples could be one, the house where love had started, and one where the house where love had ended. So as you can see that the common sense symbols for house where love had started is love, life, marriage, passion, and romance, which is totally semantically inconsistent with our metaphoric symbols. So here the correct replacement is the house where love had ended and not the house where love had started. So to summarize our automatic creation of parallel data, we first identify sentences with metaphoric verbs from the Gutenberg poetry corpus. We then convert them to literal using masked language models and also employ adapted knowledge model COMET to ensure for semantic meaning overlap. This way we have parallel sentences metaphorical to literal. Next, through this process, we created a parallel data of 90K training and 3K validation. So we start with a sentence, and then we use MLM and COMET to replace them to its literal counterpart. So as you can see here, for the input, that wounded forehead dashed with blood and wine is converted to that wounded forehead covered with blood and wine. So now here we use the literal input as an input to the encoder of BART, and then the metaphorical output acts as an output for the decoder of BART. And this is how we fine-tune the BART model. Now, once the model has been fine-tuned, that is trained, we use a discriminator, which is a metaphor detection rescoring model, which is trained on an independent metaphoric data. And we use this as a discriminative model to re-rank the beams we output from BART. So as you know that BART would output the beams based on traditional likelihood-based approaches. What we do is we take all these beams and then we re-rank them based on the discriminator's metaphoricity scores. So for an input, the black desert covered in iron silences, our output will be the black desert gripped in iron silences. So for intrinsic evaluation, we rely on multiple sources, one from the data set of Mohammed et al., and one from sentences from the Reddit subreddits of writing prompt and OC poetry. We randomly select 150 examples, and we additionally ask literally expert to also generate metaphors. So the baselines employed for our task is one is lexical replacement, which uses MLM and COMET without the BART fine-tuning. The second baseline is a metaphor masking state-of-art model used by Stowe et al. And finally, we also use the fine-tuned BART model without our discriminative step. So for automatic evaluation, we rely on semantic similarity with the literal input using SBERT for meaning. And we also employ BERT score between the generated and the human written metaphors. For human evaluation, we evaluate on the criteria of fluency, meaning preservation, creativity, and metaphoricity. And we ask crowd workers on Amazon Mechanical Turk to rate our outputs on a scale of 1, which means worst, to best, which means 5. So you can see the automatic evaluation results. So here, the human one is, of course, best, which is consistent with our idea that humans are typically best in these tasks. But our mermaid model actually does pretty well compared to our other baselines. When it comes to like human evaluation results on Amazon Mechanical Turk, we see that the human one outperforms every possible system, which is kind of expected as they are expert. But our mermaid model actually does better than all the baselines, and also human too, which is pretty surprising for us. So for our task-based evaluation, we collect poems from the OC Poetry subreddit, and we limit to only 4-sentence stanza. And what we do there is we replace the literal verbs in the poem with the metaphorical verbs from our mermaid model. And then we ask Turkers whether the original version or the rewritten version is better. So as you can see here, the mermaid version wins 68% of the time compared to the original model, which wins 32% of the time, which shows the efficacy of our model. So to summarize, what are we still missing? So we are missing more theoretical insights. That is, we haven't incorporated the conceptual metaphor theory, which is the most important theory of metaphor in our work. So conceptual metaphoric theory holds that we use conceptual mappings between domains to generate linguistic metaphors. So metaphoric mapping typically consists of source and target conceptual domains, where the source domain is the conceptual domain from which we draw the metaphorical expressions, while the target domain is the conceptual domain that we try to understand. To give you a more clear example, if you take a classical mapping, argument is war, where if you had an input, they argued against the contract, you could change this to they fought against the contract. Or for example, if you had an input, they supported their new proposal, you could change this to they defended their new proposal. And this is handled in upcoming ACL paper